Welcome to the Math Show with Mr. DeClerico. This video is about two things. One, statistics, the discipline of gathering, presenting, analyzing, and making conclusions about data. And Murphy's Law, the principle that anything that can go wrong will go wrong. We're going to talk about how to incorrectly gather, present, analyze, and make conclusions about data. In other words, we're talking about stats fails. Let's start our discussion on gathering data. There is a correct way to do it. Identify a population you like to study to begin. Say we were a little maniacal and we were going to do a study on Furbies. We would want to find actual Furbies for our study, not whatever on earth this is. Yeah, let's avoid uncanny AI disasters like this. Once we've identified our population, we want to identify a topic of interest pertaining to that population, like, No, we're not doing that. What is the most popular color for Furbies? Now we can actually collect some data. We randomly select a sample that does a good job representing the population, which in our case would mean we go to our favorite toy store, times a few, and we go to the Furby section and collect our data. And we would glean the information relevant to our topic of interest from our sample we've collected. So we record the predominant color of many Furbies and make a conclusion from there. Wow, gathering data is easy. What could go wrong? Well, suppose you wanted to save a little time and energy and just go to your local toy store. That would be convenience sampling, which is when we choose an easy-to-find sample which almost certainly will not represent the population. We need to look at many stores, not just one. The next couple of follies are all about a nasty four-letter word we see in statistics: bias. Surveys suffer from bias when results don't match reality because either 1, the sample we're working with doesn't match reality in the first place, or 2, the sample is not providing accurate results. We like ourselves a good representative sample, or a sample that resembles the population. To borrow an analogy from one of my betters, consider the population to be like a bowl of chicken noodle soup. If we wanted to sample this population of soup, we would want a bit of each of the ingredients in proportion to how they appear in the bowl, not just a bit of chicken and a bit of noodle. That would be kinda silly. But unless we're on our statistics A game, non-representative samples happen all the time. Suppose now you're going to pivot and conduct a new study, which involves a new population. You're going to study the 90s kids in your town, and you're going to ask them a simple question. Do you like Furbies? You take to your laptop, you make the survey, and you send it out to everyone who's willing to take it in your town who's born in the 90s. But that's a voluntary response survey, which means you're going to get voluntary response bias, which means that the sample self-selects. You don't select it. People who want to take your survey take it, and people who don't, won't, which means that strong, often negative opinions are going to prevail. People like this guy are going to be like, nah, I'm not doing this. But people like her are definitely going to take this survey, and they're going to leave a strong negative response, which means that the results of your survey are going to be skewed towards, you guessed it, strong negative responses. To avoid this, you could whip out the old phone book, sample a bunch of names of people you think are born in the 90s, and send them a message via snail mail to fill out your survey. Then you can follow up with these people and make sure that they take the survey. But some of the people are exceptionally hard to reach because they're busy living their best life overseas with their boatloads of money. Your sample is said to suffer from undercoverage, which means certain subsets of the population, who may have different opinions than others, prove especially challenging or impossible to survey. People who are either exceedingly wealthy or exceedingly not wealthy are chronically undercovered. Suppose you were to consider a different question. Does your Furby still work? Yes or no? Say this individual got that study and she thought back to her time with Furbies and realized that her last memory with a Furby involved a blowtorch. which she is not proud of. So she responds to the survey and she says yes, which is obviously a lie. Uh-oh, that's response bias, or the tendency for respondents to answer in ways that are misleading or just flat out false. Alternatively, she could just decide not to respond at all. But, uh-oh, that's non-response bias. That's when subjects do receive the survey, so they are not undercovered, but they choose not to take the survey, and their opinions may be different than those who choose to participate in the study and take the survey, so it is bias even if they don't respond. Their opinion might be different than others who choose to take the study. And here's the worst part about all this. If we have bad data, we can do all the correct mathematical analysis we would like, and our result will be hot garbage. As an analogy, suppose you had rotten food. You could follow the recipe as well as you would like, but you're only going to get something you're going to throw in the trash. Let's talk about graphs. We can use graphs to show how frequently different values occur in a set of data. Pie charts are especially good for part-to-whole analysis. If our data are numerical in nature, we can use a special kind of bar chart called a histogram. If each bar corresponds to only one possible value, the chart is said to be ungrouped. But if each bar corresponds to one of several possible values, it's said to be grouped. If our data involve two variables we suppose might be related, we can construct a scatter plot and then construct a line of best fit as a predictive tool, which is a small feat for your graphing calculator. Wow! Displaying data is easy. What could go wrong? Well, suppose for a moment that you were sick, but you took meds. You're monitoring a fever, and you have enough wherewithal to create this data table. This is a graphical representation of the change of your body temperature, with temperature on the y-axis and time in minutes on the x-axis. And so is this. But how? Focus on that y-axis. The range of temperatures on the graph that suggests very little change in my body temperature includes a lot of temperatures that cannot support human life, and therefore this graph is hot garbage. However, this graph only features temperatures that can sustain human life, so this graph is much better. Here's another data display featuring the grades of 5 students I've taught, except no. You might think that Marco is really pulling ahead from the pack until you look at the y-axis. This time, I should actually expand my y-axis to include all passing grades. That gives the correct idea that each one of these students, not just Marco, is really doing a great job. Fixed it! There's another less than helpful graphical representation that, in the US, shows up about every 4 years. It looks something like this, which strongly resembles a Republican landslide. But someone on the internet's gotta say it. Here's an ugly but significantly improved data display of the same information by Mark Newman. Each state, in its size, is made proportional to its representation in the Electoral College. This demonstrates what you might call the area principle. The area of a data display should correspond to the value it represents. Mark fixed it. If you've been around the channel for a while, you're familiar with this guy. Independence. Two events are independent if the occurrence of one doesn't affect the likelihood of the other. Take 2 dice, for example. One die roll has no effect on the other die roll, so we say that 2 die rolls are independent of each other. However, if we were to, say, pick a club and not replace the card, our odds of picking a spade, or any other card, would be changed. That means that picking a club and picking a spade, if we don't replace the club, are not independent events. Probability becomes really easy when we assume events are independent, but we can't always do that. We need to talk about dependent events. Suppose we're in the medical field and we're doing some research on the success rate for 2 different procedures. Procedure A has a success rate of 80%, while procedure B has a success rate of 75%. Walter, someone in our study, needs both procedures, so I guess we can assume the odds they both work are 80% times 75% is 60%. So Walter has a 60% rate of success for the combined procedures. Well, actually, no, we can't assume this, because we don't know if receiving procedure A could alter the likelihood of success for procedure B, or vice versa. We cannot assume those events are independent necessarily. Now, just to give you an idea about how sneaky independence versus dependence is, a very similar question was proposed to this individual, Marilyn Veaux Savant, who boasted an IQ over 200, and she accidentally assumed independence in her answer. This is of course not to dunk on Marilyn and her intellectual abilities, she's way smarter than any of us. This is only to say that we need to be very careful when computing probabilities. Let's talk about some bad experiments, shall we? Say we wanted to research the quality of baby's best diapers, as opposed to the competition. We would be comparing the quality of the baby's best diaper versus some generic alternative. And our variable that would determine which diaper is better could be, how well they do what diapers are supposed to do? That's not quantifiable. Average time before changes required. That's quantifiable. So how could we perform an experiment? Well, perhaps this is one way we could do it. We could apply a baby's best diaper to one baby and a generic diaper to another baby, and we could just time it and see which diaper lasts the longest. Well, if you've been awake in a statistics class, you know that this is a bad idea. There should always be multiple subjects in the control and treatment groups. This principle technically is called replication. So we replicate with a respectable 15 babies in each group. However, we forgot to consider whether some of these babies have moved on to solids. Well, that's a problem, because a well-designed experiment should eliminate possible confounding variables, which are variables that we're not studying that may have an influence on our results. This principle is called control. We could do a study that only featured babies who had not moved on to solids, or we could do a study on babies who had moved on to solids, but that limits how widely applicable our findings would be. So if we want to maximize how applicable our findings would be to include all babies, regardless of their stage, here's what we could do. If we knew there were 20 babies in the study who had not moved on to solid food and 10 who had, we could make sure the treatment group and the control group had proportional representations of each type of baby. This would make the confounding variable solids versus no solids a non-factor. This technique is called blocking. So replication and control fixed our problems? Looks like no. Remember, confounding variables are variables that we're not studying that may have an influence on our results. How do we know that we've handled all the confounding variables? Is the unaccounted for confounding variable just a fact of life we're going to have to deal with? Of course not. When it comes to mitigating the effects of confounding variables that we don't even know about, statisticians have an ace in the hole: randomization. Here's a confounding variable that we haven't considered. Does the presence of a food allergy necessitate a diaper change more often, or less often? Suppose we had no way of knowing which of the 30 babies in our study had food allergies. Here's what we could do. We could assign a number to each baby, 1 through 30, then use a random number generator like the one on your calculator to produce 15 values from 1 through 30 at random. Those 15 could be assigned to the treatment group wearing a baby's best diaper, and the other 15 would be in the control group. That way, even though we didn't know which babies had allergies, those kids would be randomly dispersed between the groups, which limits bias. Talk about an ace in the hole. There's no harm in stacking a couple strategies that we know work, and randomization plus blocking, when it makes sense, makes for an awesome way to reduce bias. Remember how we split our sample according to whether they've moved on to solid food or not? We could randomly assign half of the solids block and half of the no solids block to the treatment group, and the other halves of the blocks to the control group. This would account for the known confounding variable directly while accounting for unknown confounders indirectly. But here's another equation we should acknowledge. Replication plus control plus randomization equals a lot of work. An experiment demands a rigorous and thoughtful process. And even if we do all this, we can still take an L if we regard the results of our one study as gospel truth. The results of one study, even a good one, amount to weak evidence. We should be cautious to endorse a result that isn't supported by multiple well-constructed studies. And I would be remiss if I didn't talk to you about how people can use real, verifiable, bona fide statistics to deceive you. What if I told you that these two numbers refer to the same quantity? Well, that's kind of strange, because the first is a small proportion, and the second is a big number. It would help to know that 1 million is 2% of 50 million. That is a true fact. And if we're talking about a total of $50 million in question, that would be valuable context. Now imagine a world in which we did not have that valuable context. You have now entered the world of detached statistics, which is our world. Let me explain. Suppose you're going through the supermarket, just being a consumer, and you notice something that gives you some nostalgia. Your favorite childhood cereal, now with 10% less sugar. Wait a second. 10% less than what? Than a cupcake? Oops, I missed that little tiny asterisk. Contains 10% less sugar than the leading brand, which is? Okay, time out. What's the purpose of that 10% less part? Is it A, to inform me about the sugar content per serving relative to the cereal I grew up enjoying on the daily? Is it B, to inform me about the sugar content per serving relative to some other cereal I should know about? Or C, to entice me to buy the cereal? Yeah, it's that one. Now, the cereal actually might have 10% less sugar than, I don't know, something. But since we lack the context necessary to understand what 10% means, it's a detached statistic, so we should regard it as meaningless. For another example of deceptive statistics, let's talk about rookie phenom Adrian Sanders, who's been putting up some pretty impressive numbers recently, so by the end of week 7, sports analysts are taking note, and the organization who hired him is starting to say things like this. Though weeks 1 through 3 were not necessarily glamorous. This is an example of cherry picking, which is when we strategically choose values to support a preconceived claim that may or may not be actually true. All is certainly not lost for Sanders, though, who, even despite his first 3 weeks, is averaging just shy of 65 rush yards per game, so he's on pace for 1,100 yards this season after 17 games. And the management is still quite pleased with their running back. He's injured. This is the problem with extrapolation, which is when we predict output values for input values beyond those included in the data. This is not so much intentionally deceptive as it is just irresponsible, but it's still deceptive, let's be real. To close, we're going to discuss the most famous stats fail, if you ask me, which could only be thinking correlation means causation. My goodness, this happens all the time. Suppose we wanted to answer the question, do rooms with more trash cans tend to have less litter? Well, how could we answer this? We could go to a couple of buildings, explore the rooms in the building, and see how many trash cans each room has. Then see if there's some kind of association between the number of trash cans in a room and the amount of litter. However, we notice something a little curious. As the number of trash cans per room increases, there appears to be more litter, which must mean that an increase in the number of trash cans causes an increase of litter? Wait, hold on. That's a double error, friends. First off, correlation doesn't imply causation, which means just because things are related does not mean that one caused another to happen. Also, we're taking a hands-off approach in this study. We don't have control and treatment groups. That means this is an observational study, which can never, ever, ever show causation. Only an experiment can do that. Just so we're clear as mud, an experimental study employs a hands-on approach. We divide subjects into a control group and one or more treatment groups with the question, does the special treatment change results? We determine if the treatment group behaves a bit differently than the control group. Throughout the process, we're able to control the environment so that we can only conclude that a change in treatment is responsible for a change in outcome. Therefore, correlation can show causation if we do it right. But we're not doing an experiment in our study about the trash cans and the litter. We're performing an observational study, which is a hands-off approach. We observe variables that might be related and draw conclusions about an association between variables. In this case, correlation can't show causation. Think about it. This silly conclusion, may have something to it. But how do we know that the causation isn't reversed? How do we know that more litter doesn't mean more trash cans? More likely still, it could be that more litter and more trash cans are related to how much food there is in the room, which we're not studying. A variable that we're not studying that makes it look like two variables in an observational study are related is called a lurking variable. The biggest problem here is since we can't control our environment, we have no idea which of these scenarios is the most accurate. All is not lost, of course. An increase in the number of trash cans is associated with an increase in litter. That much is true. Whether it's causal or not is a different matter altogether. Because correlation doesn't imply a causal relationship necessarily, and an observational study can never, ever, ever show causation, because you never know if there's a lurking variable in your midst. Why is stats so easy to mess up? The process is exhaustingly rigorous and sometimes expensive, which makes cutting corners easy and tempting to do. It's also easy to deceive people with things they don't understand, which makes stats a black box from which you can pull whatever result you want, slap a number or a graph on it, and people accept it. We need to be humble when doing or citing statistics. Statistics is powerful in its ability to explain relationships and make predictions. But since most folks don't have a deep understanding of statistics, it's also a powerful motivational tool that can be exploited by activists, politicians, businesses, and that one uncle at family gatherings. As a wiser uncle observed, with great power comes great responsibility. Fail to use statistics responsibly, and you'll end up with results like this. Thanks for watching The Math Show with Mr. DeClerico. Be sure to click subscribe, hit the like button, and all that good stuff.